Okay, so I think it's already a time, and first I would like to thank Professor Dario Poletti from SUTD for agreeing to talk in Quantum Machine Learning Journal Club. And this is the second talk of the third iteration of Quantum Machine Learning Journal Club. And Professor Poletti works at SUTD, as I mentioned, and he has been actively working on machine learning techniques for quantum problems. And today he will talk about tensor network-based machine learning of non-Markovian quantum processes. So Dario, the floor is yours. Yeah, please proceed.
Thank you, Kishore, for giving me the chance to talk about this work. And thank you for everybody who joined this Zoom session. So as Kishore said, I've been working on machine learning for a while. There are two main things that I've been doing. One is of this flavor, where we use techniques inspired by numerical methods inspired by many-body quantum physics, and particularly tensor networks, to do machine learning. And the other one is a collaboration that I've been having with Christian Miniature and Stéphane Bressan, and on using neural networks to study many-body quantum systems. And so today I'm going to talk about this side of the my work on my machine learning. Okay, so let's start. Does it work? Okay, good. So I'm going to try to give you an idea of how we want to describe open quantum processes, and with this idea of the process tensor, and then how it can be represented as a matrix product operator. I will explain what all of these terms mean, and then a circuit model representation of a generic process, open quantum process. And then I will show you how we can learn these things with NPOs, matrix product operators, and in particular, we'll show you an implementation of a open quantum systems and how we learn its properties. Okay, so this is the idea. Let's go for it. We start with telling you about open quantum systems and process tensor. So let us consider a quantum system S. And then we put it in some environment, okay? And the quantum system may be a quantum device, or something like a quantum computer or a quantum sensor. And of course, you would like to know whether it keeps its performance as it is in contact with an environment. And so it is important to characterize the influence of environment on the system. And okay, if you have been playing with the available quantum computers, you will know that they're noisy, although most of the noise may be characterized by classical sources of noise, not quantum sources of noise. But you know that noise can be a big problem. Okay. So how does environment or yourself can affect a system? Okay, so there are different ways in different things. The evolution of the system is dependent on. One is the coupling to the bath and its properties, maybe the temperature of the bath or the type of coupling that you have with the bath. Okay, and also, you know, as the system progresses, you may want to do some preparations on it. Okay, or apply some unitary protocols or even some dissipative protocols on it. And also you can make measurements, and the measurements will affect the while every operation that you do is on the system itself, it will affect the overall density matrix of system plus environment, okay? And this may have some repercussions in how the environment is affecting the system later on. So both preparation and measurements have an important role in how your system is going to evolve. And this is a little bit different from classical mechanics, where you can do, the measurements will not have such a critical role. Okay, so let me try to describe what we could do. For example, we can take a system and doing some preparation. For example, we have a two-level system, and we every certain while time dt, we make it point down, okay, for example, but it's always in contact with an environment. And after a while, you can make a measurement. And then you can do this many times. You do this at time t1, you do t2, t3, all the way to tn, okay? And so this should be quite a general, fairly general scheme of things, as long as you're doing your measurement and your preparation at discrete times. So how do we describe this? We take a system, which I characterize here by like this circle with a 0 inside. And then I connect an environment as a chain. It could be, the system could be a spin and the environment another spin chain or something else. It doesn't matter. You just have a fairly large Hilbert space, okay? So you have a system, and overall your system plus the environment form this rho 0, your initial condition. Then system and environment together evolve, okay, because they're coupled. And so we have like a free evolution of the system plus the environment, which I denote by this free evolution here, E of dt, okay? And after that, I may want to do some measurements and some preparations. I may want to measure what the system is and do some preparations. And then I will do some evolutions again free evolution as before, other measurements and preparation, and so on and so forth. Now, if you look at this system in detail, this whole process in detail, and you remove whatever you do yourself, for example, the initial preparation of the system and all the other measurements or preparations, you are left with what we call, and it's called in the literature, the process tensor. Okay, and as you can see here, it ends up being a tensor with a number of legs, which are basically these gray legs that come out here. Okay, let me see, there is maybe a question in the chat. No, hi Mirko, the evolution does not need to be adiabatic. We don't do any assumptions on this. Oh, another question, sorry. Okay, no, it's just the same question. Maybe I put this here. Okay, so if you have questions, let them come in the chat. If I recognize that they're happening and they're coming, I will try to address them. If not, I will address them later on. So try not to lose me now because this is a critical part. Okay, so we have no assumptions on the adiabaticity or not of the evolution. Okay, so we have some evolution and all of this. So you see the effects of the environment, all the spins that we had before, okay? And all the free evolutions, okay? They all can be put together into a large tensor. And this is what we want to learn, because this is what describes all the possible processes that they can occur. If we can learn.
There is a question from Quick, like, is it a one-shot measurement?
Ah, okay. So once we see the circuit model later on, we can get to that. It is actually general. We can try to do different types of. For this would be yes a one-shot measurement, but we can also do other things. I will get back when we see the circuit model. You can have an idea of some of the things that we can do with this. Okay. Thank you. Okay, let's continue. So how do we represent these process tensors as an NPO? So for those of you who are not familiar, I'll give a little introduction on MPS and MPOs because I will need them because it will be my numerical tool to do machine learning later on. Okay, so if I consider a large many-body system, okay, for example, L spins, okay, sigma 1 to sigma 2 all the way to sigma L, each one with a dimension in local Hilbert space of dimension D, okay? If I want to describe my wave function psi, I will need the number of coefficients C, sigma 1, sigma 2, sigma L, which goes as D to the power of L. And this becomes quickly unmanageable. So one idea that came out effectively in the 90s is to describe these coefficients as a product of tensors. And what is done is that you limit the size of this tensor to a large enough number that allows you to describe accurately the most relevant part of the wave function. Actually, for certain type of problems, this is an exact ansatz, okay? And especially for 1D system with local Hamiltonians. For other systems, this may not be exact, but you may be able, for example, when you do time evolution, in general, this is not an exact answer, but it may still allow you to describe the quantum system for long enough times. And a very good review for this type of problems is in Annals of Physics 2011 by Uli Shorrock. Whenever I would say that for 1D mini-body quantum systems, this is the way to go, is the best method around. Okay, as soon as you go to two dimension, things get a lot more complicated, and there is no clear winner yet, especially if you want to do time evolution. If you want to do ground states, Monte Carlo can do very good things, but there is also other issues. Okay, so this is the idea. Instead of representing this vector with an exponentially large number of coefficients, actually you need a polynomial large number of coefficients if you think of it as a product of tensor. And one way to represent this is to use this graphical representation, which I try to introduce you now because I'm going to describe it. For those of you who attended my talk in this quantum machine learning group 2 years ago, maybe this sounds familiar, but I don't think that there is many people who have been there 2 years ago. So I'm going to show you this again. I think Kishore remembers this maybe. Okay, so we have this matrix product state. Now you can think of it that each component with 3 legs like this is a local tensor, and then he has one leg which is physical. Yeah, Mirko was also there. One leg was physical and 2 legs which were which are auxiliary indices. And by summing together over the auxiliary indices, you get your coefficient for a certain choice of sigma 1, sigma 2, sigma 3, sigma 4, and sigma 5. Now, once you have this representation of your quantum state, then you can also represent operators which act on this state. And these operators will be something that looks like this, which have 2 outgoing physical legs and 2 auxiliary legs. Okay, and you can imagine that your state, for example, your sigma 1 will act on this sigma 1, and you come up with a tau 1, and so you will have you can describe all the possible operators acting on the matrix product state. Okay, so now you can see already there is some similarity between this matrix product operator and what is going to be a tensor process tensor later on. Okay, for this, I'll try to give you this description I was trying to tell you, the similarity between the process tensor and a representation as an MPO. Because you look, all these legs here, for example, the red portion, this is typically an MPO that acts on the MPS, which you use to describe also your density matrix. MPS can also be used to describe density matrices. And you can think of going from left to right. Actually, can you see my mouse? Is it visible? Is it clear?
I mean, it was visible, yeah.
Okay, good. So you can use to go from left to right, but actually you can think of it of going from the bottom up, which is actually the way we do the calculations. We start here, you can think of it, you have all of these actually represent kind of an MPS, and then we build up on top of this, and we end up with everything what is represented here below by the epsilon, which is a tensor, because we have an MPO, because we have 2 legs here, and 2 legs here, and 2 legs here. So you can write it up like this. And this is what we want to learn. What we're going to do, we're going to give a different input state and different and then we're going to measure what are the output states. And from there, we're going to infer what the process tensor is. Okay. Is this clear so far? Okay. So let me continue with the circuit model. And so for some of you, maybe what I said, it was a bit abstract, but maybe when you see the circuit model, it will speak more to some of you. Okay, so let's say I have a set of preparations, which we will do randomly. We will have like different random 2-level systems that we prepare. And then we have our environment here. And then we send our first state inside here. We do the evolution of our system plus the environment. Then we get out, we do a swap. Okay, we send in the next one and we take out whatever we had. Okay, and then this continues to evolve, and then we send another state and we do a swap, and so on and so forth. So what we get outside here is a reduced single particle density matrix here. This is just what we choose to do here. What we could do also instead would be just to do a particular measurement here, maybe in a random direction as well. Then we will need a lot more data to get more information. But this is also a possible thing. We just do here one measurement and see what happens. And it can be just, we don't have to do an average. Okay, we just, whatever we get out, we measure, we see what happens, and we continue. But of course, we get less information than if we were getting just the density metrics here. That is what we're doing because we're just doing numerical simulation. We are planning to do now all of these calculations on a true quantum computer and see what happens. Thanks to IBM. Okay, so this is the idea of how we will run simulations either on a quantum computer or how we simulate it on our classical computers. But keep in mind that now the system is actually, let's say if you have an environment of a certain number of spins, let's say L, and now we have a certain number of preparations, the overall system that we're studying is is given by one spin for each preparation that we have plus the environment, okay? And all of them are density matrices. So quickly also this becomes quite difficult to manage numerically, okay? But okay, we can manage, we'll look at not too large system and we can manage that. Okay, so I hope this is clear how we want to do the circuit model to represent and to study this. And by learning, by giving different x1, x2, xn, we just choose many different random possible inputs. And by looking at the density metrics that we get out, we learn, we train our MPO and we try to learn it. Okay, so this is how we do it. Okay, if you think about it though, you may wonder how much memory do you need to do this? And actually, the first thought you could have is that if the number of the size of the inputs is d to the x and the size of the output is also d to the dx, then you will need a dx squared to the power of n. But in reality, what the whole memory that you need is what goes through this thick bond here, okay, this auxiliary dimension here. And this is mainly bounded by two things. One is the number of spins that you have in your environment, okay? So if the environment is given by only like 5 spins, this will not be more than 2 to the 10, okay, in dimension. So 2 to the 5 squared because these are density metrics. But also you can think that the environment may be Markovian enough. And then in the case that a lot of the memory of previous processes will be lost very quickly. Okay, if it's Markovian, will be lost very fast. But you know, it may decay, and so this will will limit how much actually memory you really need to do this. And this is what we want to learn. This is something that we could learn by understanding what is the bond dimension. By measuring what is the bond dimension that we need here, we can figure out how much memory is required in this process to describe it well, okay? Or whether maybe even it is Markovian, okay? So this is something that we can learn. And we can learn very well in using MPOs. It's a very natural way to do this because the bond dimension gives you exactly that quantity. Okay, so let me tell you how we're learning the process tensor. And this is related to a paper which I presented to you 2 years ago. Okay, so I will go a little bit faster, but we still try to give the main point that we did in collaboration with some computer scientists in SUTD and with my former PhD student. And so the idea came from some papers by Stoudemire and Schwab, and also by Wang Lei and Pan Zhang in China. And they've been using tensor networks as exponential machines, basically, instead of linear networks to learn various to solve classical machine learning problems. Okay, and so we thought of doing that to do also to do machine learning, but basically to do sequence to sequence learning. Okay, so given a sequence, we can learn another sequence. And the way we do this is given here. We have a sequence of different inputs, let's say x1, x2, x3, x4, x5. And we have an output sequence, y1, y2, y3, y4, y5. And whatever they are, we can always describe them as vector and turn them into matrix product states. Okay, and then we can use these matrix product states to train an MPO. Even if the problem is non-linear, okay, we can always do that. Then in some cases, this learning method will work very well. And actually, it works very well also for some diffusion problems, non-linear diffusion problems we tried. And it worked very well for some strange cellular automata that we also tried. But it may not work. It may not work very well in general. We tried some strongly non-linear maps, couple non-linear maps, and for that it wasn't working very well. But it can work, and it will work very well in some problems which maybe are quantum in nature because the structure is very natural for it. So we take some input data, some output data, convert them to MPS, and use that to train an MPO. And then this is how you do the training. And to do the prediction, we take input data again. I'm trying to move something. Okay, never mind. Can you see the capital X and capital Y, or is it blocked by something?
Yeah, capital.
Okay, very good. All the way to there, very good. Okay, so we put in the input data, we multiply by our MPO, we get as output an MPS, and then we use a process inverse to the conversion of a vector to an MPS to convert our MPS to an output vector. So this is the idea. It's fairly straightforward. There are some things, of course, you need to be careful if you want to implement it in a way that works, but the idea is fairly straightforward. Okay, so okay, I'll describe this. So for example, let's say if we have an input that can be 0, 1, we convert it to a vector in this way, normalized vector. And then if you have a sequence which is like one hot vectors, we can also, or we have larger numbers, then we can convert it to one hot vector. So we can always do that. And then we can describe our vector as an MPO. It will be a trivial, MPS. It will be a trivial MPS with one dimension 1. And then we train the MPO. This is the interesting part. So the way to do this is we build a cost function. Also, this is not particularly original. We have the exact output, and then the predicted output, the y bar, which is the multiplication of our MPO times the input. Okay. And then we have a regularization term. This term is extremely important. Without this, your prediction would be terrible. So you will have this hyperparameter alpha, which actually plays an important role in the term. If you put it to 0, you have no hope to getting good results. Okay, so you have to adjust that. And I mean, maybe this also can be done automatically, not from the outside, but that is very important. And then you just do a minimization procedure, which is similar to computing the ground state of many-body quantum systems, because we have the natural structure of MPSs and MPOs. So we take our cost function, and we do the partial derivative with one of the tensors of the MPO, and then we set it to 0, and then we sweep across. So we do it for the first, and the second, the third, and the fourth, and then we sweep forth and back in a similar way in which you compute the ground state of a quantum system. And this will give you very good results because, okay, to give you a bit more details, this problem here becomes a linear problem, and you can solve it with either exactly or with Lanczos methods to get approximations of your MPO. Okay. And after that, you do the prediction, and once you have you have some data input, your train MPO, you multiply it, and you get an output. Okay, And later after that, as I described, once we have the MPS, which has a certain bond dimension here, this is a step that can be done in many ways, and various optimization can be done here. You have an MPS with a with a finite bond dimension here, larger than 1, and you want to approximate as best as you can with an MPS of bond dimension 1. This is also not difficult. Just do a minimization process, and you find the MPS of bond dimension 1 that best approximate this. It's all linear problems. And then you can easily convert this back to a vector. So this is the procedure if you're interested in the numerics, how to do this. Okay, so now let's implement this method that we built before with these new ideas of the process tensor to try to learn an open process tensor. Okay, so we prepare one spin system and 3 other spins, which for us will form the environment. Okay. And the environment will also couple it to a buffer. So you can think of it as like a super environment, and which will allow us to change whether the environment is Markovian or not, or more Markovian, and, or at least to be more precise, will allow us to change the time scale over which the environment memory is lost. Okay, so let's go into the details. We have a full Hamiltonian of system and environment, which has Hamiltonian system, Hamiltonian of the environment, and Hamiltonian of the interaction of system and environment. Okay, the system will just take a single spin, so we'll just put a simple sigma z operator. For the interaction, we couple our system, site 0, to all the spins of the environment. You see, there is a sum of all the terms. And we chose to have a coupling of the type XX coupling, okay? Why? There was no particular reason, just to have like some tunneling. It could have been also a different type of coupling. These choices are not particularly fundamental, okay? It's just an example of an application of this idea, how to do this. And the environment, we choose to have an environment which has a magnetic field in one particular direction, and then some xxz in xxz terms. And since there's 3 of them, they're all talking to each other. Okay, this will allow the environment to mix enough within itself, whatever information or whatever correlations are formed with the system. And as I said before, we couple this to the environment only, to a buff. And for this, we decided to have a simple Lindblad buff, which can try to fix the polarization of the environment spin. Okay, so it would try to fix with this parameter R how much the environment spin will tend to be down or up. But this gamma here will be a rate at which this happens. So if gamma is 0, then there is no decay, no dissipative process in the buff. If gamma is non-zero or large, but not too large, then the process it will decay fairly fast. If it's very, very large, then you can go into some quantum zero processes, and that is a completely different physics. Again, we don't go in that direction yet. So there is a question from the audience: what is the delta? So let me try to go back one slide here. This delta is in the XXZ chain is called anisotropy, and indicates, in a sense, how strongly interacting the system is. Okay, so I hope that it's clear what we have. We have a spin, we have an environment, and we have a buff coupled to this environment. Okay, and we made some particular choices here, but they are not particularly fundamental. The one thing to keep in mind is that the system spin is coupled to all the buff spins, and that the buff is also coupled to, so the environment is also coupled to like a super buff, which make it relaxed or something. Okay, tries to make it relaxed or something. Okay, so let's go to what we observe. Okay, and here I'm going to, in this heavy slide, sorry for this, I'll try to describe to you what are the things that we input and then what we're trying to observe. So first of all, we input all the prepared density metrics for the system, which we rewrite as an MPS, and because of that, I put in this form here, just to indicate that I turned them into MPS. And then we will have as output different reduced density matrices. Okay, and this will be the output. Okay, so at different individual times. Okay, so we have different indices here. The top index indicates which realization of our circuit this is. Okay, so for which realization of inputs we are considering. And the bottom index, here small n, indicates the time at which the measurement step that we are looking at. Okay, so when we have 1 to n, it means we're considering all the different measurement steps together. And if I look at only n, it means that if I look at the circuit model here, I'm looking, for example, only at one particular, like y2 or y1, okay? So this is one thing we look at. Then we look at the overall output, of course, and then we also try to look at the overall process tensor, okay? We know what the process tensor is because we produce it. And so we can see whether we train well, and when we train, we learn well the process tensor. Now, one thing that we need to highlight though is that when we run our simulations and we train our MPO, the outputs that we get may not be physical density matrices, okay? And this makes things a little bit difficult to compare, because when you compare a non-physical density matrix with the physical ones, then you find very, very weird results. So we do an extra step before we compare the output. We, given the output of our the input states times MPO, given the output, reduced local reduced density matrix, we find the density matrix which is physical density matrix which is closest to it, and this is what we call this capital Y cal here, Mn, and this is what we use when we compute distances, okay, for the single density matrices. Okay, so I hope it's clear what we are measuring and what we are trying to estimate. We're trying to estimate the output, local density matrices, the overall output of the density matrix, and we are trying to also measure whether, see whether we're learning the process tensor itself well enough. Okay, so let's continue. And how do we measure whether we're doing a good job or not? When we look at this at the infidelity, which is just 1 minus the fidelity. Okay, and in the plots here that I will describe in detail in the next few slides, what I'm going to show is all the lines represent the median infidelity that we measure. Okay, and you want the infidelity to be very small. Okay, so small values is good, and the width of these curves is an error bar, which shows what is the 95th percentile confidence of finding the values inside there. So you only have a 5% probability of that the output is outside of these error bars. Okay. So we have standard definition measures for fidelity, and we look at the infidelity, and we look at the median one. So let's look at different possible cases. Okay, in these plots here, what we show is the infidelity versus the bond dimension of the MPO that I use. Okay, because I can try to train with different MPOs, and in general, you need large MPOs to represent well the state, but maybe small enough MPOs can be good, especially if the system is Markovian. You know, the one dimension one would be sufficient. Okay, so you may not see it here because it's a little bit hidden by this blue box, but it's transparent enough. You should see that these things are dependent on bond dimension D, and we're changing the bond dimension of our MPO. Okay, now the different curves represent a different dissipation rate in the buff. So as I said before, gamma equals to 0 means all the evolution of our system plus environment is unitary. There is no resetting, there is no dissipative process acting on this overall system. And so the buff can have a very long memory. And in this case, you see, is the highest curve. The infidelity stays fairly high, even if we increase the bond dimension. We need a much larger bond dimension to keep a good fidelity. This is a signature of the fact that there is still quite a bit of memory in the system. As you increase the dissipation rate, like 0.25, 0.5, you notice that smaller bond dimension, even like bond dimension 4, or if you okay, yes, let's say 4, will give you can give you a very accurate representation of your states, because the infidelity is going to be low. I also would like to point out why, you may ask, why does it stop around 10 to the minus 6? Okay, what is this error here? And actually this error is due to our numerics, because even just for the evolution of the system, we do numerical methods, and our accuracy in the evolution of the exact one is actually to 10 to the minus 6. So when we're here, this is like a threshold. We cannot do anything better than 10 to the minus 6, okay? Because this is as accurate as our training input data are, okay? So this is the one thing that we can change. For example, we can change the rate of dissipation of the buff, and this is the results, which make a lot of sense. We can also try to change how the buff is trying to set up the system. For example, for R equals to 0, maybe I go back, show you this term again. Okay, for R equals to 0, the buff the buff tries to so the environment tries to set the buff in the up states or everywhere. So you will have a pure state in the buff. But for 0.5, the environment, the super environment, is trying to set the buff to like infinite temperature state. Okay. And you can imagine that maybe the infinite temperature state has a smaller memory. But here, because of the limitation, okay, given by the fact that we're using a finite gamma, we don't see a particular difference here between these three different scenarios. Okay. The next step is to look at the strength of the coupling between the system and the environment. This famous J here, which I can go back, I'll show you again in the Hamiltonian, is this term here that couples your system with all the spins in the environment. Okay, here we see that for small system environment coupling, it's a lot easier to learn the process, because you can imagine this would be almost unitary evolution of the system, okay? Especially if the time scale at which we're studying here, the time scale we're using are fairly small. The environment has no time to play too much with the system. But as we increase J, okay, for example, J equals to 4, and we need a much larger bond dimensions, okay? Although the numbers are not crazy, so bond dimension 10, to achieve a low enough infidelity. Okay. The next thing we can look at is exactly what I was telling you just now, this issue of time. For example, how frequently am I doing the measurements? If I'm doing the measurements very frequently, there is hardly any evolution, and especially the environment has no time to act on the system. And then you will see that very small bond dimensions are enough to have a very, very accurate description of your system. And as you increase the time, then the system and environment get more and more correlated, and you will need larger memory to describe your system. So all of these things are hinting to us that we are learning our processes fairly well. Then I can also try to look at how many samples do I need to train properly my MPO and to get good infidelities, I mean low enough infidelities. And here, the main point of this figure is, as you can imagine, that it depends on the value of your bond dimension that you have in the MPO. If your bond dimension is 1, so you're basically assuming the process is Markovian, your infidelity will still be very high because we chose parameters of the evolution such that the process is non-Markovian. And even if you train with more and more, you will not get any better because you chose a terrible ansatz, okay? You don't have enough possibility to take care of the correlations and enough memory for this evolution. As you increase the bond dimension, you're able to go lower, but if your bond dimension is not large enough, you eventually hit a plateau or how accurate you can be. And here, for what we are showing here, for bond dimension 10, we are able to, even with 900 training samples, we can still learn. We're still learning and we're still improving on our results, okay? So this tells you about the expressibility of your of the ansatz, okay? And this is also maybe if you want to use this to learn something, you should do your simulations with different bond dimensions so that you can you know whether you're being accurate, you're still learning or not, or whether the results have converged, okay? Okay, so this is important, and only if you have a large enough bond dimension, you can really profit of many training data. Last one is maybe a little technical, but not so much. When we were looking at the infidelity, we were looking at average fidelity of across times. But maybe you can think that we are learning well the first times because the evolution is fairly simple, the system is not very Markovian, and maybe later times we don't learn so well, and because the process, overall you need more memory, the system is more complex. This is not true. The way we're doing the learning is such, and with the sweeps, is such that the infidelity IN, so for each different time, across times, and this is the different 6 time steps, is fairly constant for whichever bond dimension we use, whether we use bond dimension 1, the yellow curve, or 4, the blue curve, or 10, the red curve. The learning is, the accuracy of our prediction is fairly the same across times. Okay? So it doesn't improve as time progresses. Okay. Now we can also go back to the idea of how much we are learning depending on the bond dimension that we have. And here we are trying to look, instead of the single reduced density matrix, I look at Y, all the output. So the all output of Y from time 1 to time n versus bond dimension, okay? And I try to look at as I train from 500 to like 4,000 training data, okay? Now, as we learned before, if we need larger bond dimension to be able to have a better accuracy in your prediction, so smaller distance, okay? And if you don't have a large enough bond dimension, then it will reach a plateau. And actually not really a plateau, as you can see here, but things can get worse. And this is basically a result of overfitting, okay? So we can learn well all the outputs, okay? But we need a large enough bond dimension, and we will see when we get if you train, you will see that you improve, and then you get to a minimum, and after that you start to improve, or fairly constant and a little bit improve, because you tend to do overfitting. So then you know where your limit of your prediction are for a given bond dimension for your MPO. The same, you can do it for the full process tensor. Here I look at delta epsilon. So epsilon is the full process tensor. I can ask anything out of the process tensor later on. I can say, okay, what will be if I put any other measurement or inputs or outputs that I consider. And here again, we will see the same effects. For larger bond dimension, we can predict our epsilon better, but it gets worse. Okay, we will get into overfitting if you keep training when you don't if your bond dimension is not large enough. Okay. And with this, I go to my conclusions. So process tensors allow one to describe generic quantum processes, open quantum processes, and specifically they are very suitable when you can do both preparations at different times and measurements at different times of measurements. What you get out is this process tensor. And it has a natural representation as an NPO. And so it's quite natural to think of using an NPO-based machine learning algorithm to learn it effectively. And this NPO can tell you a lot about the properties of the process. And in particular, by looking at the bond dimension, it can indicate how non-Markovian the process is. And then we are in the process, no, we are in the very beginning process of trying to do these simulations now on IBM machine. Let's see what happens. So for this, I would like to thank, very importantly, Kavan Modi, who is in Monash now. He used to be a CQT years ago. I know some of you know him. He is the one who had the idea of thinking of using the tools that we developed to learn the process tensors. And then, of course, I need to thank Gochu, who is a professor now at Yunnan Normal University, and who did all these calculations. And previously, Alantier and Weilu from SUTD, who asked me to do the first version of the NPO learning algorithm. Okay. Okay, thank you very much.
Thanks, Dario. Like, that was a very nice talk, and his audience will have many questions. So there is one question already from Thiprat. He's asking that how does your training results depend on the initialization of NPO?
Ah, so we have a guest also from Thailand at the moment. Is it very nice? Hello, Tip. It doesn't really depend because once you do the training, so what you want to choose is maybe something that is as close as possible to the solution. But even if you don't know, it doesn't really matter, because as you go along this minimization process, you should be getting very close to the ground state. It's like when I do maybe I try to compute the steady state of a system using this system. Oh, he's here in Singapore. Okay, very good. When you do these systems, you unless the energy landscape is very weird, you're very likely to get very close to the correct solution. So I don't think so far I haven't seen major problems. When I was studying some frustrated systems, okay, and my initial condition was too close to some of the possible ground states. You could get into some issues, but with a bit of experience, you should be fine.
So now if somebody has a question, like, they can directly like unmute themselves and ask, like, because we have some time, and please proceed.
I have a question then. Okay, Dario.
Yes.
When you train your process tensor and you get all the weights, okay, in the end, okay, is there any kind of structure that emerges? That is to say, or do you have, some links that are not populated, if I may say so? Or is it, essentially all the weights of the same order of magnitude or whatever? Is there a simplification in the structure that you get?
Okay, so if there is an emerging simplification, this will be due to the properties of the process. What I can tell you is that the number of variables, okay, actually really can change during our process. So as you know, when you do MPS minimization, for example, for ground states, you set the maximum one dimension. But if the singular values that you have, you only need a few singular values, then you will truncate up to a certain, you will truncate all the singular values which are smaller than a certain epsilon, okay? So it will already remove everything else, all the auxiliary indices which are not necessary. So the bond dimension there is not always that's the maximum that we allow. Okay. Okay, so yes.
Is there any question from anyone? Okay, Dario, very nice talk. Like I have, like a comment kind of question. Like, so it seems like, the goal here is that, you want to learn this process tensor or MPO. And this reminds me, like in classical machine learning or learning theory, I should say, people are interested in basically learning some hypothesis or some function, which basically maps inputs to outputs.
Mm-hmm.
And then, like one is often interested in, not having their hypothesis class or the function class very strong. So they add some regularizer, like which you also have to make it, not the model capacity very large something. Now, but then, like the power of such hypothesis class or function classes are measured by, like there are many parameters. One of the way they measure it something called VC dimension. So VC dimension is the way, like for example, linear classifier, like linear classifier in dimension D has VC dimension like D+1. So for example, if I give you 3 points, like you can find a line which, like classified. But if I give you like 4 points, then with a line, it might be difficult to not classify them in a two-dimensional plane. Now you have analogous notion of this bond dimension. I mean, there might be some connections with the VC dimension, which people look in computation, like computational learning theory with statistical learning theory with the notion of bond dimension that, I mean, which people use in many body physics and which you are using here to, look at how complex the learning would be. Like, I mean,
okay.
Make some insights related to this.
Okay, I'll try to give you some comments on this. When we started to work on using MPSs and MPOs for machine learning, I mentioned that there were these two works in the physics community. But later on, we discovered that there was a work also in NLP from a Russian group. I can find the reference for you. I think we cited. And they refer to these systems as exponential machines, linear exponential machines. But what the point is that, of course, you cannot represent an exponential large number of systems. The number coefficient at the end of the day is d times d squared times L. Okay, so this is how much you can play with. But the nice step is that is in the minimization procedure. And this is also why DMRG works so well to study the ground states of a quantum system, is that despite the Hilbert space you want to analyze may be very large, okay? It is able to find a portion of describe very well a portion of the space, which gives a very accurate description, okay? And so this is, they call it, for example, also for time-dependent problems. At the beginning, some of the algorithms were called time-adaptive DMRG, okay? Because, okay, there is a portion of the space they can describe, but they twist around in a way that they're able to get as much of the relevant portion of the Hilbert space were described, okay?
Hi, can I say something myself, Kisho?
Yeah, sure, please, yeah.
Hi, Dario. We don't know each other, but nice meeting you.
Okay, hi.
Electronically. No, I just wanted to add a comment on this thing, which is that between 2004 and 2010, there were plenty of papers to assess what is the faithfulness of the MPS representations, yes, and also the PEPs and the MIRA structures, okay? And there were theorems, so we have very solid results. And essentially, because the MPS is the one that is trying to correlate one qubit with the next in a sequential way, it turned out that the theorems matched perfectly with the entropy of the system. And you can see that if if the entropy is of the order of the log of the number of qubits, then the representation is faithful in an exponential way. So
Yes.
you have you can approach exponentially close in any measure of norm to the state. Okay, whatever. Is it a time evolution? Is it a ground state? Whatever. It's just about the ability to represent the state.
Yeah.
Then it turns out that you can be exponentially accurate if the system only has a log entropy. Okay, actually you can. The chi is related to 2 to the entropy. So we do understand in which situations this can be applied.
Yeah. And I think recently there has been also works for steady states that try to tie this also.
Sorry, I missed the word. For what? For what?
Steady states. Steady state in open system also now. There have been works in this direction.
Yeah. And for time evolution, it was immediately seen. There are papers by Fazia and other people that evolution grows linearly in standard systems. The entropy grows with time linearly. So very soon, MPS will no longer be relevant. Okay,
yeah.
it will stop describing.
In general, true, yes.
Yeah, in general, even for the Hamiltonians of the type of Ising, if you don't start from stationary state, then they developed linear entanglement linearly in time. Although there are Hamiltonians which are much more efficient in building entanglement, these fast scramblers that people use in black hole physics. Okay, so I think there was a lot of understanding of the how much you can simulate. Actually, there was this paper I remember from Garching where they made a simulation with cold gases, and the best simulation of the time evolution was done with MPS at that time. So we know that it has limitations, but so far it's the best we have.
Yeah, I think you're referring to the Scholbach and Bloch collaboration,
yes,
right?
That's correct.
2012, I think.
Emmanuel Bloch
yes.
did the famous graphic where you could follow with MPS the evolution up to a time. No, but it was much better than other things.
Yes, indeed. Yes, this is true. We of course, if in general it's not possible to describe time evolution, but there are, like, for example, we did some works where we were trying to do some effective Hamiltonians and fast driving, such that the system is always close to some kind of ground state, and then the state that it was always manageable. So it depends on the, of course, on the entanglement entropy within the state and how it scales.
Yeah, no, I always thought that nobody has tried to challenge supremacy, okay, advantage with tensor networks, which is the most natural thing to do.
No, actually, we did that.
You did? Okay, so
we had a PRL last year.
Okay. How far could you go?
We did 7 by 7 by, I think, 8. We used this. Okay, but we need to talk in detail of what gates we were using, right?
But you try boson sampling with?
No. It was a random random circuit, and we used Tianhe, which is a supercomputer in China, and it's a collaboration with some people in China. I can send you the paper.
Okay, please.
Yeah,
please.
No problem.
Yeah, and it was also mentioned in the beginning when these approximations are well known to be good for some Hamiltonians, and there are also the mathematical theorems by Hastings.
Yes, I could have been much more precise on that. Sorry, thank you.
By Hastings saying that frustration-free Hamiltonians are.
Yes.
Good.
Yeah, sorry, thank you.
Yeah. That was quite insightful, I would say. Yeah. So, are there any more comments from anyone or questions? Okay, if not, then let's thank once again.
Salut Dario, merci.
Dario?
Merci.
Thank you.
And next week, like on 29, we have Professor Latore speaking about his research. So I will send an email to everyone very soon, like in a few days something. So thanks a lot for joining, and thanks Dario for giving such a nice insightful talk. hopefully there will be many research work coming related to this in future. Yeah.
Thank you. Bye.